In this video, we will be talking about the universal law of gravitation, Newton's universal law of gravitation, and I'll do a quick explanation on this formula and what these variables mean. So, let's talk about the gravitational constant. First, the big guy out of all these. So, the gravitational constant is 6.67 times 10 to the power of negative 11. And if you're curious, the unit for the gravitational constant is newtons times meter squared times kilograms squared. Now, this doesn't really matter that much, so you could kind of ignore it if you want, the unit at least. And what do the masses stand for? M1 and M2. Well, you can have, let's say you have two balls, 5 kilos and 3 kilos, and their masses of 1 and 2. So you can assign them, well, this could be mass 2 as well, and this could be mass 1. Doesn't matter which one you assign mass 1 and mass 2. And these masses are represented in this formula here. And r is the distance between their centers of mass. So r is just the distance between the two ball centers of masses. And you might be thinking, well, intuitively, you're thinking, it doesn't make any sense. These 5 kilogram balls, 3 kilogram balls, they're not big enough to have any gravity. I thought only planets had gravity. Well, no, everything in this entire universe has gravity as long as it has mass. You can calculate the force of attraction between these two objects, actually, using this formula. And this force basically explains to us, well, how much force are these two balls pulling at each other. Now, if you're on Earth, air resistance will likely be stronger, and it'll probably resist, or friction even, will probably resist these two motions, so they just won't move at all, even over time. But basically, this formula just describes and tells you the force between two objects based on their masses, the gravitational constant, and the distance between their two centers of mass. Let's go ahead and do some problems that have us calculate the force between two objects, or the gravitational attraction. All right, so we've got a simple problem here. And all you're doing is evaluating the magnitude of gravitational force between two 5 kilo spherical balls. So maybe I'll draw this out for you guys. Maybe, just maybe, I'll draw it out for you guys, just to help you understand what you're looking at, because physics is it's a pretty visual subject. And we have a distance of 15 centimeters here. Well, 15 centimeters is 0.15 meters. So let's keep that in mind. You always want to use meters and kilos. And all we have to do is, well, plug it into this equation. So it's a simple problem where you just plug things in. Teaches you how to use it. So gravitational constant 6.67 times 10 to the power of negative 11. Your mass, the masses of two objects, is 5 kilos and 5 kilos. And the distance is 1.15 meters squared. So once you evaluate this, you should get a final answer of 7.41 times 10 to the power of negative 8 newtons. Now, this is a very small number, but as I've said, no matter how small the mass of anything, gravity has a force. And this force for these 5 kilo balls are very, very small. It's 7.41 times 10 to the power of negative 8. Now, in this problem, sort of the same thing. We just plug answers, but part B is more conceptual. So let's plug in. Let's plug in what we know. So obviously, we need to plug in the gravitational constant, and we need to multiply the mass of the ISS, which is 370,000, times the mass of the person, 150 kilos, what's suited. Okay, and she's 20 meters away from the center of mass, so this squared, 20 squared. So the force of gravity from the ISS and the person is equal to, I put a dot, 9.25 times 10 to the power of 6 newtons. So this is the force of gravity, which is still very, very small, even though the ISS is very large, 370,000 kilos large. But okay, how about for part B? How accurate do you think your answer would be? Well, I'm not really going to write anything down for this because we don't need to. I'll just explain. It's not going to be that accurate because the ISS isn't uniform in mass. So I guess the center, so you'll be pulled in some direction, like the wings. I don't even know what it's called, the wings of the satellite, and you'll be pulled towards the center in the control panel of the living space, whatever it's called. You'll be pulled in different directions. So this answer likely isn't accurate, but it's a somewhat approximation of what you would be experiencing, assuming that the ISS is a perfectly uniform sphere. So for this problem, it's slightly longer, and we're going to have to include a little bit more details and use our knowledge on Newton's second law of motion. So this problem, we have an asteroid, Totatis, and it passed near Earth in 2006. Very relevant detail, by the way, at 4 times the distance of our moon. This was the closest approach we'll have into 2060. Another super relevant detail to the problem. If it has a mass, so the asteroid has a mass of 5 times 10 to the power of 13 kilos, what force did it exert on Earth at its closest approach? Now, you're not given the distance of the moon in the problem, and you're also not given the mass of Earth, so I Google searched it for you guys, and I wrote it down here. So just a little bit more work, less work for you, since you're already probably suffering from this class. But what was the acceleration of Earth? Oh, oops, I skipped a part. What is the force of gravity that they exert on each other? So let's use your gravitational, universal law of gravitation formula. So as always, put down the gravitational constant, and we multiply the two masses of the objects. So the mass of the Earth is 5.972 times 10 to the power of 24. And we multiply this by the mass of the asteroid, which is 5 times 10 to the power of 13. And their distance is 4 times the distance to our moon, so we need to multiply 384,400,000 squared. So 300 times 4, sorry. So the distance is times 4. So it's 1.54 times 10 to the power of 9. There you go, meters. So once you evaluate this, you should be getting a force of 8.42, approximately a force of 8.42 times 10 to the power of 9 newtons. Well, now that we solve for the force that they're exerting on each other, we can solve for parts A and parts B. So what's part A? Part A is, what is the acceleration of Earth caused by the asteroid Totatis? That is the very similar to the last name of my algebra teacher. Caused by an asteroid Totatis in its closest approach. Okay. Well, we have the force that they're attracting with each other, and Newton's second law states force equals mass times acceleration. So this is a very simple calculation. Divide force by the mass of an object, and you should get the acceleration. So we're trying to calculate the acceleration of Earth. So we need to calculate the force, which we already did. So the force is 8.42 times 10 to the power of 9 newtons, and then divided by the mass of the Earth. So the mass of the Earth is 5.972 times 10 to the power of 24 kilos. And once you divide this, you should get an acceleration of 1.41 times 10 to the power of negative 15 meters per second squared. So Earth is barely accelerating towards this asteroid. Asteroid's doing absolutely nothing to the Earth. Oh. Okay, well, what about part B? Let's see what the Earth is doing to the asteroid. So the force of gravity is still calculated by the universal law of gravitation, which is 8.42 times 10 to the power of 9 newtons. And now we need to divide this by the mass of the asteroid to get the acceleration. So force divided by mass equals acceleration. So we divided by the mass of the asteroid, 5 times 10 to the power of 13 kilos. And you should be getting an acceleration of 1.68 times 10 to the power of negative 4 newtons. Now, that is still an extremely small number, maybe not as small in magnitude as 10 to the power of negative 15, Oh, oops, not newtons. Yikes. Yikes, 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 yikes. This is meters per second. This is meter per second squared. This is meter per second squared. Still quite fast. No, still quite slow of an acceleration. Asteroid is barely getting pulled towards the Earth, and that is due to the fact that universal law of gravitation has an r squared at the bottom. So distance squared exponentially decreases the force of gravity over a distance. But as always, I need to mention OpenStax. So OpenStax, free online textbook. Link will be in the description. I get my practice problems from there. But if you thought what I said in this video helped, consider subscribing and liking the video. And as always, if you have any questions, put it down in the comment section. Thanks for watching.